Assalamualaikum warahmatullahi wabarakatuh, and we are from group 5, and this is the video presentation for the group assignment Convolution. This is my team, which is Azhar Arif, Ahmad Amru, myself, Nur Yasmin, and Yu Kong Yuan. Objective of our task is for gain a comprehensive understanding of utilizing convolution to analyze the relationship between input and output in linear time invariant algebraic system. Second, to develop the ability to calculate system response accurately, and lastly, to acquire a practical skill in implementing numerical convolution technique and generating plot using MATLAB to visually represent the input, impulse, response, and output. The methodology that we use for task 1 is required to write a MATLAB program for the two signals provided in the question, which the signal must regenerate to confirm the accuracy before proceeding further. This signal represent as S1t and S2t. Well then, undergo addition and conversion operation when they are needed to be calculated manually. The result of the operation will be validated using the modified MATLAB program. Additionally, the output of the conversion theorem is denoted as YT, but the result of the addition operation is expressed as ZT. Task 2, we are required to analyze the system output signal YT, which begin solving the signal FT step by step. First, the cosine graph and unit step function are drawn. This signal then multiplied to obtain the graph, which subsequently multiplied by HT produces the graph of the unit step function, where we use the conversion method to get output signal YT.
Okay, so now we'll talk about the task 1 for signal and system assignment. So for the first row, we set the time length. So for the second one, from row 3 until row 12, is for the figure 1a. So the MATLAB cannot directly use the unit step function, so we need to set a variable into a time. So as the row 4, we set the variable ut is equal to the time bigger than 0. So same as the row 5, we set ut1 equals to the time is bigger than 1. So the row 7, y1 is the unit step function of the figure 1a. And from row 8 until 12 is the function to plot the graph. So same as the figure 1b, we will set a variable, for example ut plus 1 is the time more than -1, and then the y2 is the unit step function of figure 1b. So same as the above, row 19 until row 22 is the function to plot the graph. So from row 24 until row 35 is the additional function of the figure 1a and also 1b. So same as the things before this, so we need to set the variable into the time. So this is the additional unit step function. From row 37 until 44 is the function to do the convolution of figure 1b and also 1a and also b. So this row is the convolution function, and this row is we will set a new time length for the convolution graph, and 40 until 44 is the function to plot the graph. So now we will run the coding. Okay, so this is the graph for the first part coding. So this is exactly the same with the left sheet. So this is for the second coding part, and this is for the third coding part, which is the additional function of figure 1a and also 1b. So this is the fourth part, which is the convolution theorem of 1a and also 1b.
In the signal addition, we have the two equal x1 to x. We have the t equal x1t plus x2t. x1t is a rectangular signal as we have, and it's x2 is a rectangular signal as we have, and so we have to add the amplitude of each part of time, or each duration of time. So at t equal -1, the t equal x1t plus x2t equal 0 plus 1 equal 1, and at t equal 0, the t equal 2 multiplied with 0, which is 0 plus 1 equals 0. At t equal 1, the t equal 4 minus 2 plus 1 equal 3. At t equal 2, the t equal 0. So after we have this all this amplitude, we will draw the new signal, which is like this. We determine this. We determine the new values that we have, and then we draw the signal. Convolution, we have yt equal x1 convolution x2. This is x1 is a rectangular signal, and x tau is the same, and we need to make the rectangular signal x2 to be x2t minus tau, and draw it like this with the new values. So we have that the evaluation y2, the convolution y2 equal x1t convolution x2t. That means that it's the integral of x1 tau convolution x2t minus tau dt. From negative infinity to infinity. So that we have like fixed cases. In case 1, when t plus 1 less than 0 and t less than -1, we draw the new graph like this. This when t less than -1, and t plus 1 is less than 0, and the common area between them is 0, so integral is equal to 0. Case 2, t plus 1 is bigger than 0 and less than 1, which is here, and t is less than -1 and bigger than 0, which is here. It will be equal to 2 squared plus 2t plus 1, and less than 2, and t is bigger than 0 and less than 1. The common area is here, and the convolution or the integral will be equal to -2 square plus 2t plus 1. In case 4, when t plus 1 bigger than 2, less than 2, bigger than 2, and less than 3, which is here, and the common area will be here. So the integral, the integral will be equal to -2 square plus 2t plus 1. In case 5, we have when t plus 1 is bigger than 3 and less than 4 here, so the common area will be here, so it will be equal to 2 square minus 6 2 plus 9. In case 6, when t plus 1 is bigger than 4, which is here, the common area is not, there is no common area, so the integral of y2 will be equal to 0. So y2 will be equal to these intervals, and then we need to draw the graph, and the graph will be like this, and it's the same as the MATLAB.
So now I will explain how to analyze the inputs in FT and the system response HT, and step by step. Let's start with FT. The inputs in FT is given that today is a rectangular pulse with a width of 1/2 on both sides, centered at t equal to 0. Ut equal ut minus 1 is a unit step function difference, which defines FT as non-zero only between t equal to 0 and t equal to 0.25, because the tau is 1/2. Since it's 1/2, when we divide by half, the positive side 0 to 0.25. So by combining these two parts, FT is a pulse that starts at t equal to 0 and ends at t equal to 0.25 with an amplitude of 1. Outside this range, FT equal to 0. So FT is effectively a rectangular pulse between t equal to 0 and t equal to 0.25. So now let's analyze the system response HT, which is given. So for the first term, 1.5, ut minus 1.5. Ut starts the signal at t equal to 0 and negative ut minus 1.5. ends it at t equal to 1.5. This creates a rectangular pulse from t equal to 0 to t equal to 1.5 with an amplitude of 1.5. For the second term, negative ut minus 2 minus ut minus 2.5. So for ut minus 2 starts a negative pulse at t equal to 2 and negative ut minus 2.5 ends it at t equal to 2.5. So this results in a rectangular pulse from t equal to 2 to t equal to 2.5 with an amplitude of negative 1. So combining the terms from t equal to 0 to t equal to 1.5, ht equal to 1.5, while from t equal to 1.5 to t equal to 2, ht equal to 0. And then from t equal to 2 to t equal to 2.5, ht equal to negative 1. Outside this range, ht equal to 0. Thus, ht is a piecewise signal with two distinct poles. Ft is a rectangular pulse from t equal to 0 to t equal to 1, and ht consists of two rectangular pulses, one positive from t equal to 0 to t equal to 1.5, and one negative from t equal to 2 to t equal to 2.5. This will be used in convolution to determine the output signal yt.
Okay, we'll continue for the case to get the result of yt. So for the first one is case 1, which is t less than 0. For t less than 0, the signal is not overlap. So we'll given the result of yt, limit of infinity until infinity, f tau, ht minus tau, d tau, we'll get the result of 0. So the limit of t is 0 until 0.25. So we'll give the overlap of the two signal from 0 until t at the screen. The yt is equal to 1.5t. Next, for the case 3, the limit of t is 0.25 until 1.5. We'll get the result of 0.375. Next, for the case 4, 1.5t until 1.75 for the limit range of t. We'll get the result of negative 1.5t plus 2.625. For the case 5, the limit range of t is 1.75 until 2. So we'll see the graph is no overlap for the two signal f tau and also ht minus tau. So we'll get the result same which the case 1, which is 0. For the case 6, the limit range of t is 2 until 2.25. So we'll see the range overlap is 0 until t minus 2. So 0 until t minus 2, 1 multiplied with negative 1, which is the ht minus tau, is already negative of negative 1 in the graph. So we'll give the result of negative t plus 2. For the case 7, which is the range of t 2.25 until 2.5, we get the result of negative 0.25. For the case 8, the range of t is 2.5 until 2.75. We'll get the result of t minus 2.75. For the last one, case 9, t more than 2.75. So we'll see at the graph which is no overlap and we'll get the result of 0. Okay, lastly, for the fully result of output yt, we need to have the result of all the yt from case 1 until case 9 and the limit for all the case. So we'll see the graph of our yt output, which is from the 0 until 0.25. It will go up with the gradient of 1.5. So the output result we get from yt is 1.5t. Next, for the 0.25 until 1.5, we will see the result is 0.375, which is the constant. So the result of the yt also constant at 0.375 magnitude of yt. Next, for the 1.5 until 1.75, the result of yt is negative 1.5t plus 2.625. So we will see that the gradient of the result is negative 1.5. Next, for the 1.75 until 2, we will see the result of yt is 0. So the result is constant at 0. For 2 until 2.25, the result of our yt is negative t plus 2. So it will give also the downward linear from 2 until 2.25, which is the gradient of negative 1. Next, for the 2.25 until 2.5, we will give the result of constant negative 0.25. So for the output of YT, show the constant of negative 0.25 for the limit of 2.5 until 2.5. Lastly, for the 2.5 until 2.75, it will give the result of t minus 2.75. So it will linear upward from 2.5 until 2.75, and t more than 2.75, 2.75 and above, it will give the result of 0 for the YT. So it will show the result of YT that they given at the screen. That's all from me. Thank you.
So the things that we can analyze from the given assignment is that in task 1, the input signal must be illustrated using a MATLAB code, where additionally, calculation for the addition of the signal should be performed and compared within the result from the MATLAB code written for the same operation. The convolution theorem will be applied to perform multiple operations on the two signals following the same method as the addition operation to verify the accuracy of the result. While in task 2, the convolution formula is used to calculate the output of the LTI system based on the given input, signal and impulse response. The results are derived manually, ensuring accuracy and precision as the system's output is determined entirely through the convolution formula applied to the input and impulse response. To conclude the assignment, in task 1, the results are obtained by developing a MATLAB program for the addition operation and using the convolution formula for the convolution result. While in task 2, the output signal is determined manually by applying the convolution theorem, the input and impulse response signal provided. All calculations in task 2 are done without MATLAB, ensuring accuracy through manual method. That's all from us. Thank you.